welcome back everyone. So it's pretty cool. It's actually shifting and working much better than my previous F1 gearbox model. So I'm super stoked about this. On this video, I just kind of want to give an overview of the electronics and the actual control algorithms that are controlling this. Obviously, this has been a build series, so please go back and check out my previous videos if you want to know more about how seamless gearboxes work or why they have two shift barrels and all the other details throughout the build from the hardware perspective. So just a quick overview of the hardware. I actually ended up using the same PCB that I created for my active suspension test rig. At the heart of it is an ESP32 microcontroller. I have a TCA9548A, which is just an I2C multiplexer. And the only reason for that is because I have two AS5600s, which are magnetic encoders mounted to the back of the stepper motors. And those only have one I2C address. For actuators, I'm using two NEMA 17 stepper motors. I've chosen to drive them a little bit differently than I've done before. I'm actually using two L298N motor drivers, which are typically used for brush motors and things of that nature. But I'm actually using them to drive the individual phases of the stepper motors themselves. And I'm actually using a library for Arduino called SimpleFOC, which stands for Field Oriented Control. The biggest advantage with SimpleFOC is that it's a closed loop stepper control. And this is very important when you're working with essentially a dog clutch gearbox. And that's because if the dog clutches, the teeth on the dog clutch is perfectly aligned, you need to do is actually keep pressure on that slider so that it engages the gear as the gear is sliding past it. Stepper motors, if they don't have some sort of feedback mechanism, will just miss steps, and you'll say, hey, move 60 steps. It'll move 60 steps, but it won't realize that 5 of those steps were missed and didn't fully engage the gear. Luckily, the SimpleFOC library is fully built for handling all of this, and you can see you can actually back drive the motors and they will try to resume their previous position so that you essentially can't get in a bad situation where you potentially engage two gears at once. And then the other motor I have in here is just a simple geared motor. It's set for 500 RPM at 12 volts, but I'm actually controlling it via another L298 motor driver. And that is mainly because I have to do a little bit of a throttle cut to allow the teeth of the slider and the dog clutch on the gears to actually disengage for just half a second as I'm pulling the slider off. It just helps the shifting be a little bit more reliable, and this is something that they use in real gearboxes as well. And I think I forgot to mention this. Another cool part about the SimpleFOC library is that I can use a lot more voltage. So most of the stepper drivers today, they do allow you to go to 24 volts or so, but I was able to actually use up to 36 volts, or actually 30 volts through the L298N. Which just allows me to be able to accelerate the stepper a little bit faster. And then the SimpleFOC library, I'm actually using what they call space vector control. This also allowed me to get some very dynamic response from the stepper motor itself. Again, it's not ideal. I'd like to come back at some point when there's not a chip shortage and actually build my own brushless motor drivers. Okay, so on to the actual control algorithm and software. So it's actually a fairly simple control algorithm for this particular gearbox. I decided against making it controlled from like a remote steering wheel or any of the additional things like the gas pedal that I had in my previous gearbox. I'm going to really tailor this just towards being a desktop model for right now. The first thing to do from a shifting control standpoint, the easiest way to control the position of the shift barrels is to put everything in neutral, measure where the actual angle of the AS5600 encoder is for both shift barrels, and that's essentially your offset that you use for all the other shift positions. I've actually just for simplicity created an array that has essentially each gear, so 0, which is neutral, all the way through 8th gear, and I've actually stored the radian value for the position of that gear so that I can just pass that to the SimpleFOC control algorithm and it moves the shift barrels to that position. So when you have a single shift barrel, you don't have the ability to control how closely the engagement and disengagement of two gears are. It's always going to be the same, regardless if it's an upshift or a downshift. It has to be big enough that the slider doesn't accidentally hit the dog clutches, and it just allows a few milliseconds of potential time in movement of the slider. So with a seamless gearbox, what you're doing is actually disengaging and engaging the next gear at the exact same time. And most of this is actually the air gap. So this is the gap that's between the slider and the teeth on the gears themselves. And so what you're going to do is you're actually going to start disengaging and at the same time beginning to engage the next gear and kind of take up that air gap, so that the second that the current gear is disengaged, the next gear is essentially sliding into place. For me, I actually started off testing the gearbox with essentially no phasing, and this was a huge disaster, as I'll talk about as we go further into the testing. So I've actually created this second array which stores which shift barrel is moving first when upshifting or downshifting. That's why there's actually two pairs of numbers. 0 means no delay, and 1 means essentially a full delay. So you multiply 1 times the actual delay. As you can see, there is no delay going into neutral. There's actually no delay going into first gear because only one shift barrel has to move to go into first gear. When you go into second gear, we're actually telling the right shift barrel to move first and then the second shift barrel. So you're probably wondering why I have two sets of numbers, and that's just because it's easier to essentially store it in an array because the order reverses itself as it comes back down. So the main program itself is actually very simple. It does a brief initialization just to make sure that it's actually in neutral. That's very important with these gearboxes, is you don't want to potentially have it in a position that might be locked up, like where there's two gears engaged when you start up the motor. And then it begins a shift sequence where it upshifts from neutral all the way up to 8th gear, and then it goes from 8th gear and downshifts all the way back to neutral. This is a great way of testing the gearbox, and I played with all the sorts of different speeds, accelerations. There's actually PID tuning for both the velocity control and the angular position control of the stepper motors. As you can see, some of these videos are in various states of tuning. Some of them have some overshoots where I've had to come back in and add some dampening, but overall it's literally like a tenth the amount of code of my previous F1 gearbox. It's so much more simplistic and easy to manage because of that SimpleFOC library. I mean, it handles wraparound and all the other issues with the encoders. So I actually started off with essentially no delay in the shift barrels, meaning they both started moving at the exact same time, so 100% overlap. And it actually worked really well. It would get through probably 2 or 3 complete shift sequences before it would finally lock up, and that's due to probably just a slight delay or a slider getting caught up. But what was really cool was, I actually plotted the torque output at the pinion gear coming out, and what you could see, it was less than 1/100th of a second of actual torque loss. And I think even a good portion of that 1/100th of a second is probably the gap in the actual dog teeth themselves. If the gearbox was spinning faster, this torque loss would be much, much smaller. But I had to get more reliability. If it's going to be a desktop model, I can't have it locking up on a regular basis. Where I mentioned before, I added the second array with the delay, and I found anywhere between 2 and 3 1/100ths of a second of a delay greatly improved the shift reliability and actually barely changed the torque drop on the output, which is pretty cool. So the other thing I did was I implemented a torque cut for the motor that drives the gearbox itself when the shift was occurring. So what would happen is I would actually just turn the motor off for 5 1/100ths of a second or so when beginning the shift, and that was enough to make the slider come off the gear a lot smoother and more reliably. If this gearbox was, ultra precise and infinitely stiff, you might not need that torque cut, but I know the real F1 gearboxes and almost all real sequential gearboxes still do a torque cut very similar to this. And it actually, again, increased the reliability of the shifts dramatically, and it gives them a nice snapping, popping sound, almost like a real F1 gearbox has. If you've ever seen them come down pit lane, you just hear a nice pop as it's engaging each gear. So, that's really all I'm going to do for this version 1 of this gearbox. I do plan on, someday coming back and probably adding encoders to the lay shaft and the main shaft, because one of the cool things that the real F1 gearboxes do is they actually time the shifts so that the slider teeth and the teeth on the gears perfectly align with their gaps so that they can actually fire it into the gap and there's no teeth colliding. But obviously it requires a significant amount of computing power, given that all these gears are rotating at different points and different speeds, and it has to figure out how to self-align itself, which it does through a shift testing sequence when they first start up. There's a whole state machine and a whole bunch of other stuff that has to be built. I'd also like to come back and add, like I said, brushless motors and some planetary gearboxes to shift, ultra fast and make it super reliable. The shift forks, I'd love to go back and print them out of like some carbon fiber reinforced PLA just to be a little bit stiffer, because that's really a limiting factor. But overall, I'm super pleased with this model. Shifts so much better than my previous gearbox. I really can't thank the insider enough who provided me with all the detailed information about this gearbox and a lot of information around the scaling of all the different parts and pieces. Having scaled it properly, a lot of the issues that I had with my previous F1 gearbox kind of went away, and this thing shifts phenomenally well and extremely reliable, and I actually really love this gearbox. So that being said, what about the actual model itself? So I have several hundred, if not thousands of hours into this design, but I'm going to make it all available for free on my GitHub website. I'm only going to put the step file, which is a type of a CAD file, up there. A lot of free CAD programs that are able to open this and make changes to it. I'm doing it this way because you will need a CAD program to be able to assemble it and actually go through all the parts and pieces and see how they fit together. Additionally, you're going to have to make modifications. A lot of the tolerances are fairly tight, and it's just going to be a lot easier, I think, distributing this as a step file. And if you want to make your individual STLs and whatever files you want to use for your slicers or your 3D printing, all the free CAD programs out there will support you doing that. So I am going to post the Arduino code that goes along with this as well, if you're going to try to make your own electronic controller too, to make it shift like I've done. I'm not going to post up any schematics or anything like that. I think the code has a lot of the information that you would need to do that. This is not by any stretch of the imagination an introductory or even an intermediate Arduino project. I would definitely put this more toward the advanced side of things. There's a lot of tuning that has to be done to get this to work properly, but I want to make it available to everyone who wants to play around with it and maybe make a cool desktop model like I've done here. Again, thanks for everyone coming on this journey with me. I've been really excited about it. I love these F1 gearboxes. They're, pinnacle of technology and innovation. Also, they're designed to a very specific rule set. This is not a gearbox I would use in a large number of applications, but for the particular rule set that Formula One provides and for the constraints and everything else that they do, it's an amazing gearbox. And I hope to be able to do more of them in the future, or some other kind of cool gearboxes out there. Let me know in the comments if there's other gearboxes you really want to see me build models of. Well, that's all for now. That concludes the Formula One Hybrid Era Seamless Gearbox series. Thanks for watching, and stay safe out there.